Wingtip vortices can extend behind an aircraft for a considerable distance and can prove extremely hazardous to any aircraft unfortunate enough to encounter them. The maximum tangential airspeed in the vortex may be as high as 90 meters or 300 feet per second immediately behind a large aircraft. Wake turbulence is rarely detectable, so it is very important that pilots are aware of the potential distribution and duration of vortex wake turbulence, and of the effect of surface wind speed and direction on the normal behavior of wingtip vortices. For the information of all operators, the UK Civil Aviation Authority publishes an Aeronautical Information Circular, which describes the hazard and states the approach and departure separation in time for departures and distance for approaches required between various categories of aircraft based on their weight. The AIC is updated from time to time, the most recent at the time of writing being AIC Pink 72 of 2010. Wake vortex generation begins when the nose wheel lifts off the runway at rotation on takeoff and continues until the nose wheel touches down again on landing. Wake vortices exist behind every aircraft, including helicopters when in flight, but are most severe when generated by heavy aircraft. They present the greatest danger during the final approach and landing phases of flight. And on takeoff and initial climb. In other words, at low level, and where there is likely to be a lot of air traffic. A wake turbulence encounter can lead to loss of control, and possibly to structural damage. And, if the encounter takes place near the ground, may leave insufficient time or height to recover. The characteristics of the vortices are determined by the following aspects of the generating aircraft. First, the gross weight. The higher the weight, the stronger the vortices. A shorter wingspan will cause interference between the two vortices, which weakens them. As speed is reduced and the lift coefficient is correspondingly increased, the vortices will strengthen. At any given speed or weight, the lowering of gear and flaps will decrease vortex strength. Changes in pitch attitude, which are often associated with changes in speed, will also affect vortex strength, which increases with the angle of attack. Generally, the larger the aircraft creating the vortices is, compared to the aircraft encountering them, the greater will be the wake turbulence hazard. Typically, the two wingtip vortices remain separated by about 3/4 of the aircraft's wingspan, and in still air will sink slowly and level off, about 500 to 1,000 feet below the aircraft's flight path. There is evidence that a helicopter will produce stronger vortices than a fixed-wing aircraft at the same weight and speed. Behind a large aircraft, the vortex wake can extend as much as 9 nautical miles. If an aircraft is within 1,000 feet of the ground, the vortices will sink to within about twice the aircraft's wingspan on the ground, and in still air move outward at about 5 knots from the track of the generating aircraft. Please note that the rate of movement shown here is exaggerated, and that there is, of course, only one vortex per wing. In a crosswind, if the wind is light and steady, the vortex structure will drift with wind. If the crosswind is in the region of 5 knots, the downwind vortex will drift away, but the upwind vortex will more or less stay in the same place. There are 2 possible hazards in this situation. First, for aircraft departing from the runway used by the preceding aircraft illustrated, where the vortex stays in or close to the climb-out. And secondly, for aircraft using a parallel runway downwind of the situation shown, with the vortex drifting across the runway and climb out. Similar hazards would exist for an aircraft following another on the approach. Vortices will, of course, decay with time, but the biggest influence on their dispersal is atmospheric turbulence. The stronger the wind, the more quickly the vortex will break down. The time separation minima, published in the AIC mentioned before, are applied by air traffic control, but these do not guarantee that an aircraft will avoid wake turbulence. The separation only reduces the likelihood of vortex encounter and may decrease the severity of any effects if an encounter does occur. It is worth remembering that the most serious risks occur when following heavy large aircraft at low speed in light winds, and particularly when close to the ground. If the positions of the vortex wake of a preceding or crossing aircraft can be visualized, and this assumes the pilot knows the relative position of the other aircraft, then there is a reasonable chance of avoidance. Staying above or upwind of it will usually keep you clear. However, this may not be possible or advisable during a published procedure when in cloud. So adherence to the published separation minima is the safest option. The subject of wake turbulence is covered in further detail in the Air Law and Operational Procedures and Hazards section of the syllabus.